My name is Kansuke Nunota from Osaka University. Today I'm going to talking about the systematic search for a wide orbit planet by using the anomaly detection algorithm. Okay, as discussed by previous presenter, the microlensing is one of the unique methods to detect the cold free-floating planets. The time scale of the microlensing event T is proportional to the lens mass ml. A square root of the lens mass ml. And when the lens has a planetary mass, this time scale becomes less than 1 day. Koshimoto et al. 2023 discovered that 12 events with T smaller than 1 day from 1 to 9 year survey. And this event is reported as a candidate of the free-floating planet. Also, Asumi et al. 2023 performed a statistical analysis by using these data, and they found that the planetary mass ranges are estimated to be 12 to 20 times more abundant than the star in our galaxy. This is a remarkably large quantity. However, it is very difficult to distinguish whether the contribution from these abundant planetary mass range objects comes from free-floating planets or wide orbit planets. Okay, I will explain the reason of this difficulty. This is an example of the light curve of a wide orbit planetary event. And this figure shows the geometry of the lens system and source system. When the source trajectory aligns with the line connecting the host star and the align the source connecting line of host star and planets, both the host star and the planets contribute to the magnification. So we can observe the two bumps in light curve. This is due to the host star, and this is due to the planetary planet. In contrast, when the source trajectory is perpendicular to the line connecting the host star and the planets, only the wide planet contribute to the magnification. So it is very difficult to distinguish from the magnification due to the free-floating planets. This is why it is very difficult to measure the abundance of free-floating planet alone in microlensing events. So against this background, if the occurrence rate of the wide orbit planet is accurately measured, it will lead to more precise measurement of the occurrence rate of the free-floating planets. And by using the microlensing event such which has a two bumps, the occurrence rate of the wide orbit planets can be measured. In fact, previous studies have already measured the occurrence rate of wide orbit planets. This is Polsky et al. 2022. They used the data from 20 years of observation, which consists of around 3,000 events. Among these events, the six events were identified as a wide orbit planetary microlensing event, which has a parameter of separation ranging from 2 to 6. And they conclude that the microlensing star hosts around 1.5 orbit planet on average. Building on previous study, our study has two main purposes. The first purpose is to perform the independent measurement of wide orbit planets occurrence rate using the MOA2 data. And the second purpose is to expand the orbital distance range of the previous study. However, it is in the event with S larger than 6, it is very difficult to detect the planetary signal with traditional methods. This is because traditional anomaly detection system rely on the visual inspection around the host star's magnification. But for wide orbit events, the planetary signal is too far from the host star's magnification to be easily detected by the human's eye. So this signal is overlooked. This is why the anomaly detection algorithm is required for a complete sample of wide orbit planets. Okay, let's move on to the anomaly detection algorithm. We developed this algorithm based following the Zanaito 2021. I use this light curve as an example for detail of our algorithm. Okay, this light curve has an anomaly around here. Okay, first, this algorithm performs the point source, point length fit to this light curve. Then we extract the residual from this fit. Next, we set a window for this residual. This is the example of the window. The left window contains the anomaly signal, and right window, right window is a normal region without anomalies. Yeah, this one. Next, we fit these residual using the PSPL-like model. PSPL-like model is almost the same as the PSPL model. However, while the PSPL model has three parameters, T0, TE, and U0, this model can be described by using the only two parameters, center of magnification, TC, and effective timescale, TA. In addition, we also perform the fitting by using the constant model. And we calculate the chi-square by of these two models. When the window contains an anomaly, constant model cannot explain this anomaly's bound. However, the PSPL-like model can explain this bound. So delta chi-square between this constant model and PSPL-like model become very large. On the other hand, when the window does not have an anomaly signal, this residual can be explained by both models. So the delta chi-square between these two models become around 0. So by calculating the delta chi-square over various windows, we can identify the anomalies. To identify the anomalies, we perform a grid search over TC and TL. The grid of TC ranging from a duration of the data, and the TC grid width of TC grid is 0.17 times T effective. For the T effective, this is ranging from 0.3 to 5 days, and grid width is 0.12 in the log scale. And we for the delta chi-square calculation, we only use the data within TC plus minus 3 times T effective. And this is an example of the grid search. This horizontal line shows the TC grid, and this vertical line shows the T effective grid. And this color map shows the delta chi-square between the PSPL model and the constant model. And this is another figure. So this vertical line shows the TC grid, and horizontal line shows the TC grid, and vertical line shows the delta chi-square. And in this grid, in this time, delta chi-square has very large value. And this star point shows the center of magnification from PSPL fit. So this strong signal is corresponding to this anomaly. Yeah, this is corresponding to this one. We apply this algorithm to the data alerted to event by Moat's microlink survey towards the galactic bulge. This is located at Mount John Observatory in New Zealand, and this has a field of view of 2.18 square degree. We use the data taken in the 2007 to 2022, and this sample consists of about 7,000 events. We performed the labeling by my eye, and we found that the total of around 1,000 anomalous events, and among these events, we found the wide anomaly signal in 100 events. And this is the example of the newly discovered by this algorithm. Yes. In this event, this anomaly in this event had previously been overlooked. However, by using the anomaly detection algorithm, such a signal can be easily identified. We also discovered a very interesting event with the wild signal. Yeah. This event was alerted in 2008, and two bumps were identified in 2008. Yeah, and this light curve can be well explained by the planetary model with S equals 3. However, in addition, our algorithm discovers that the event was also magnified in 2022. This event has the potential to be a triple lens system or binary source, binary lens system. If we assume the triple lens model, the separation between this host star and this magnification on this third companion is about 300. And it is the widest separation event discovered so far. Okay, this is a summary. In the future, we need to determine we labeled this label is by my eye, so we need to determine strict criteria for classifying these events. And we will perform a statistical analysis using these classified events. Yes, that's it. Thank you.
Questions? It's interesting to hear about the wide planet theory. Can you compare the order to the our solar system? What is the orbital axis, zero orbital axis of wide floating planet, wide orbit planet?
So, sorry, why
did you calculate the, for example, the semi-major axis of the
in this event? No, actually have not yet, but typical the Einstein radius is about the 2 AU or 3 AU. So this S value is this S is a value in the unit of Einstein radius. So very simple very simple calculation, the separation between these two bumps is about 600 AU to 900 AU. Yeah, so it's very wide.
Very interesting.
Yeah.
I don't actually know who's next. So. Okay, I have a question about this event too. Did you check whether this is the same source star, or perhaps there are two or more source stars blended, and you observe microlensing events on different source stars that are blended? Did you measure the centroid, whether it's different, whether the position of the centroid differs in 2008 and 2012, 22?
So you said the different source star? Yeah, I have not checked yet, but yeah, maybe I need to check. Yeah.
Hi. Yeah, so hi.
Hi.
Yeah. Because you say there's about 100 quantum orbital planets have been confirmed. Do we know their mass distributions, or we don't have any property of this kind of planets?
Sorry, well, sorry, well,
Yeah, I mean, because you say you have confirmed there's the 100.
100. Yeah.
Yes. So do we know the property of this planets?
Property of this.
Like the mass, do we know?
Those aren't all necessarily planets that are known. You haven't confirmed that those are planetary events.
Yeah, yes.
You just have anomalies.
Yes, just rather. So yeah, have to check.
So, I can't remember.
Oh.
Yeah, for Demic's question, the photometry was done, on a single centroid, and there's certainly no evidence for problems in the photometry based on that centroid in particular. I think Ian, did photometry using 2 different centroids, and I think the photometry is pretty much the same. So I don't know if it's a little challenging to exactly compare the centroids because all the stars have proper motion between, over the 14 years. So there's some noise in matching up.
Hi, do you have an expected number of these types of anomalies, even if things are not bound in wide planets? Like, given just the generic free-floating planetary mass population, how many of these types of events do you expect to detect?
For me, such a event.
Yeah, how many of these really wide ones do you expect to just see, even if they're not actually wide, they're just close in time?
Right, you're asking how many events do we expect where we see the star being lensed by a star, or the planet being lensed by a star, and also being lensed by a free-floating planet that is unrelated to the star?
Correct, yeah.
Oh, sorry, I don't understand.
It's very low. It's roughly the probability of each individual event squared. So it's 10 to the minus 12.
Okay, so then these are pretty confidently to be bound for planetary use. Okay, thank you.
So I have a question for all of the speakers that have actually made a question, something to think about. For all the speakers that we heard from today that are working on the actual data, and then for people thinking about Roman, is, for those of you that do microlensing, you appreciate that all we measure is the projected separation. So if you have you have something that looks free floating or looks wide, if there's a large population of those, then some significant fraction of the time, you're going to see them projected very close to each other, and so you'll see them as an apparently bound planet. We have an algorithm for detecting bound planets. We have an algorithm for detecting wide separation planets. We have algorithms for detecting free floating planets. How do we combine those 3 algorithms? Because they all should be self-consistent in the sense of they should all be drawn from the same population of bound and free-floating planets. I mean, you could imagine doing it with the forward model, but there might be better ways of doing that. So I leave that out there as a thought exercise for people. I'm sure people have thought of it.